Okay, this is lecture 19, and it deals with a two-degree of freedom system, or in general, multi-degree of freedom system. We started this concept on Tuesday, the previous lecture, and I would like to build upon that. And there's going to be a bit of a review in some of the stuff that we did on Tuesday. Uh, the the agenda items are down here, and first thing I want to do is remind you what the mass and stiffness matrices are in a two-degree of freedom system, and then show the orthogonality property of the mode shapes, and then we move on with the other items 2, 3, and 4 as it arises. I just want to point out that in Inman's treatment of this subject, there is a section which deals with mass normalized eigenvalues or mass normalized mode shapes. I'm not going to do that because it's unnecessary for the further development. And if you're interested, you can look at it, but it's not necessary to do the development in the course. Let me remind you that the mother of all equations for a multi-degree of freedom system or two-degree of freedom system in particular is given by that equation. In other words, minus omega squared, and omega is a natural frequency that we're supposed to find, times the mass matrix plus k, which is the stiffness matrix, times the mode shape equal to 0. We did this thing on Tuesday, and I strongly urge you to go back and look at it because we're not going to consider this thing, the derivation of this at this point. So this omega is the natural frequency, and this u bar or u arrow is the mode shape associated with that frequency. Now, what I'm going to do is multiply both sides of this equation by m inverse. If I multiply the first thing by m inverse, because this is a scalar, it gives you identity. And of course, we're going to have m inverse k times u. There we are. Okay? Now, this may look familiar to you because it's the kind of thing that you did in your linear algebra class. We have a matrix. There is the matrix. We call it A, m inverse k. This matrix I'll call A, and this omega squared I'll call it lambda. And let me remind you that this thing is actually a conventional or classical eigenvalue problem. Your job is to find lambda and u bar or u arrow, or equivalently to find omega and u arrow. Okay. Now, as I pointed out, this is the kind of thing that you have done in linear algebra, therefore it must look familiar to you. And let me go ahead here and look at this equation, this eigenvalue problem, and tell you that your math prof said that, okay, if the product of this matrix times a vector is 0, there's two possibilities. If either u bar is 0 or u arrow is 0, which is kind of useless, because after all, this u represents the deflection of the different masses, or the determinant of this must be 0. Okay? So in fact, this condition is what allowed you to find the eigenvalues of this matrix A. Now, there's one thing though. Although m and k are symmetric in this course, okay, the choice of coordinates so that it makes it symmetric, the product of m inverse k is not necessarily symmetric anymore, okay? So we're kind of destroying symmetry feature of these matrices m, okay? But in principle, we don't care. Okay, this is an eigenvalue problem, and you have m, you have k, therefore you have this matrix A, and you can solve this determinant equal to 0 and find the eigenvalues. Now, The very fact that we are approaching this thing the way I'm describing to you and making this matrix M inverse K, which is non-symmetric, tells you that it's not practical for large scale problems. We can solve small scale problems with this approach, but generally speaking, not this is not a wise thing to do. In other words, you never have to actually calculate M inverse and then multiply it by K. Okay, that never needs to be done in a heavy duty numerical calculation. Now, there's a few things that you may recall from linear algebra, and this is something that I actually need. If you have the product of matrices A and B, and you take the transpose of it, it's going to be the product of the transposes, but in the reverse order. So B transpose, A transpose, okay? AB transpose is the same as B transpose times A transpose. And the same thing applies for inverse, okay? AB inverse is B inverse times A inverse. These are things that are you should know from your elementary linear algebra class, okay? Now, what I want to show you is that the mode shapes, in other words, those vectors U associated with different frequencies or different eigenvalues or orthogonal, okay, in a very strange way. And I'll talk to you in a minute about what this thing means. So let me remind you that the mother of all equation is right here. That reminds you of your first 10 weeks of the course, mx double dot plus kx equal to 0. Okay, and we did this thing on Tuesday. We look for a solution to this equation of the form u bar. We don't u arrow. We don't know what u arrow is. E to the j omega t, or I wrote it here as I, but generally speaking, you use I and j interchangeably. Okay, good. Now, I showed you if you take this, you differentiate it twice with respect to time, because we need a second derivative of this x with respect to time, and you plug it in here, you can divide through by e to the j omega t, because that's not zero, never zero, and you get this equation. And these omegas are called the natural frequencies. And for each one of these omega, whatever omega is, for a natural frequency, you have a mode shape. Okay? Now, what I want to show you is that if we have two mode shapes associated with two different frequencies, there is some kind of relationship hold between them. So let's assume that we have a two-degree of freedom system for simplicity, and therefore there are two natural frequencies, omega 1 and omega 2, and two mode shapes. So this u1 goes with omega 1, and this u2 goes with omega 2. Okay, so first of all, because this u1 is the mode shape with omega 1, means that if I look at this equation and plug in u1 and omega 1, it's going to be 0. That's obvious, because that's what mode shape and natural frequency means. In other words, the vector u1, which comes from this equation when you replace omega with omega 1. Okay, so we know this. Let us multiply on the left, or pre-multiply it by u2 arrow. So this is true for u1. I dot it with u2 on the left side, which means pre-multiplied by u2. And you have the same thing for u2, except that I'm going to multiply it by u1. So look what happened. u1 goes with omega 1. So this equation is true, it's written here. u2 goes with omega 2. So this equation is also valid for u2 and omega 2. This equation I'm going to multiply on the left by u2. This equation I'm going to multiply on the left by u1, which means pre-multiply on the left. So if you do this and you subtract them, because u1 mu2 is the same as u2 mu1, and the same thing with with U1 KU2 and U2 KU1, because these two are the same, what you get if you subtract, you're going to get omega 1 squared minus omega 2 squared, U2 MU1 equal to 0. Now, if omega 1 is different from omega 2, this term cannot be 0. So that must be 0. So U2 MU1 is 0. And by the same token, because M is symmetric, if you transpose the whole thing here, if you transpose this, you're going to get U1 MU2 equal to 0. And the same thing is true for stiffness. So U2 KU1 is U1 KU2, and it's both of them equal to 0. Okay. So when we say the mode shapes are orthogonal, that means U2, don't dot it with U1, but dot it with MU1. So this is called mass orthogonal. And by the same token, this is stiffness orthogonal. So orthogonality, as it was taught you in linear algebra course, means find the dot product of the two vector, you're going to get 0. That's not quite what we have here. We have to put an m between them or a k between them, and you get 0 in that sense. Okay. This is what we mean by mass and stiffness orthogonality of the mode shapes. And this is critical in what we're going to be doing in the next few lectures. Okay. All right, that's exactly what I just said. Now, let's go back to our the mode shapes that we got. Remember, for the two natural frequencies, there are two mode shapes called U1 and U2. This is the first mode shape. This is the second mode shape. Suppose I take these two and put it in the columns of a matrix, and that matrix P, I'm going to call the modal matrix. Okay, so find the mode shapes, because this is a 2-degree of freedom system. This is a vector of two component. This is a vector of two component. So this first column is that, and this second column is this. Put them in the 2x2 matrix, and this is called the modal matrix. Okay. Now, based on what I just showed you, and what did I show you? I showed you that U1 MU2 is 0, and U2 MU1 is 0. Right there, you see that? I showed you that if you form this matrix, P transpose MP, literally, please write it down. So the transpose of P is just this thing, except that rows and columns are interchanged. And if you write this thing down, you see that you get a diagonal matrix. M tilde, which by definition is P transpose MP. And based on orthogonality that I showed a few minutes ago, if you literally write it down, you see that you get diagonal matrix. On the diagonal, you have U1 transpose MU1 and U2 transpose MU2. Remember, U1 transpose MU2 is 0, and U2 transpose MU1 is 0. So these things are 0. And by the same token, because I indicated that this orthogonality also applies with a k in between the two vectors, if you literally sit down and write this thing out, you're going to get a diagonal matrix. Okay? This is called mass modal matrix or modal mass matrix, and this is called modal stiffness matrix. M and K are not necessarily diagonal, but if you carry out M tilde and K tilde, modal mass matrix and modal stiffness matrix are in fact okay. Now, note, be careful. This M tilde is not the same as M1, or M2 tilde is not the same as M2. Okay, M1 tilde is this combination. M2 tilde is this combination. And by the same token, K1 tilde is not the same as K1. Okay, you can see that it's this weird thing. Okay, so just be careful that these are not the same. And that's why this is called the modal mass matrix. M is called the mass matrix. K tilde is the modal stiffness matrix, but K is the stiffness matrix. Okay, so let's do an example. This problem I did for you on Tuesday, but I'm going to repeat it. You're going to see this problem probably a few more times so that everything is worked out for you. All right. What you want to do is to verify what I just showed you. In other words, M tilde, get the M tilde, make sure it's diagonal. Get the K tilde, make sure it's diagonal. Okay, so the first thing we have to do, in lecture 18, we wrote the equation of motion for this two degree of freedom system. It came out to be like that. Okay, make sure you know how to do it. If you were in class, we talked about it. If you watched the lecture, you know what it is. Okay. Now, let's plug in these values. Okay, these are the numbers. These are the mass matrix and the stiffness matrix. We plug in these numbers, we get this. And now we find the natural frequencies. And how did we find the natural frequencies? Determinant of minus omega squared m plus k equal to 0. Minus omega squared m plus k. It's this. Just work it out. It's this. And the determinant of this thing equal to 0. Now, determinant of a 2 by 2 matrix, this product minus that product. We did this thing on Tuesday. Clean it up, you get that. And this can easily be solved, and it's got 2 roots. Actually, we have 4 roots, but we're not interested in negative frequencies. So there is omega 1, which is 2 rad per second. Omega 2 is root 2 rad per second. For each one of these 2, patiently, you have to find the mode shapes. There is no fast way, there is no shortcuts. You have to do it patiently. Okay? So these are the 2 natural frequencies. Now, literally, we're going to do it one by one and get the mode shapes. So suppose that omega 1 is 2. This is how you get the mode shapes. So plug in 2 in here, plug in M and K, solve for U1. And if you do that, you can see that if you form this matrix where omega 1 is 2, you're going to get this. This omega 1 is going to be 2, right? So it's going to be 4 times 9, 36, minus 36 plus 27, which is minus 9. Okay? This is what you're going to get. Now notice that it's not surprising that these 2 equations, there are 2 equations here, they are related to each other. In fact, if you take the bottom equation multiply by 3, you get the top equation. That should not surprise you. So we don't have a unique solution to this. We can arbitrarily set u2 equal to plus 1. I did it on Tuesday. You can choose anything you want, but I chose plus 1. And you're going to find u1 in terms of that. So we found the first mode shape, or the mode shape that's associated with this frequency, natural frequency. And repeat this where omega is root of 2. So there we are. Take this, put it in there, except that we don't have 1, subscript 1, we have subscript 2, right there. Work it out. This is going to be the same thing, except that the value omega 2 is different. And here omega 2 is root 2, so if I square it, you're going to get minus 9 times 2 plus 27, so that's going to be plus 9. Again, these 2 equations are not independent of each other. And Uh, Arbitrarily, you can set U2 equal to 1, just like I did here, and find U1, and it's going to be 1/3. So the second mode shape is right here. First mode shape or mode shape associated with this frequency. Don't call it first one. This is the mode shape associated with this frequency, and this is the mode shape associated with this frequency. Put them in the matrix. First of all, you can verify, of course, you can verify that. And I did this thing on Tuesday for you. U1 transpose MU2, just literally write it down, you're going to get 0. And same thing, U1 transpose KU2, literally just plug it in, you're going to get 0. And this is, remember, this is not the regular kind of orthogonality that you were taught in your linear algebra class. This is called mass orthogonal. U1 and U2 are mass orthogonal and stiffness orthogonal. Now, uh, the matrix P, the modal matrix, is going to be these two vectors put in the columns, and we're going to do that. Okay. So let us find the mode shapes associated with the frequencies. We did that. We did it. And then we're going to make a change of variable. So I don't like to work with X. I want to work with P times Q. Instead of coordinates X, which are the physical coordinates, I want to use some other coordinate which is called modal coordinates. So X is going to be X1, X2, which is really what I want. But I'm going to do things in terms of Q1 and Q2. And once I get on Q1 and Q2, I can plug it in here and get X's. Okay? Now, if I take the, by the way, for the problem that we just did, we know what P is. P is going to be 2 by 2 matrix, minus 1/3 1, 1/3 and 1. We know what it is. But right now, we're not looking at that example. I'm talking about in general. Okay? So if I take this, get rid of X, this is what X is. This is my change of variable. If I take this and stick it in there, you're going to get MPQ double dot and KPQ. Now, I'm going to multiply both sides of this thing by P transpose. On the left by P transpose. Now remember, we're going to get, if you multiply this by P transpose, this is what you're going to get. P transpose MP, P transpose KP. This thing, remember, we said that this is a diagonal matrix and we gave it a name, M tilde. This was M tilde, and this was K tilde. And M tilde was a diagonal matrix, and K tilde was also a diagonal matrix. There we are, okay? And look, either look at it like this or look at it like that, because that's what these things are. But the point is that these are two equations, and the first one involves only Q1 as the coordinate, and the second one only Q2 as the coordinate. And notice that this mother of all equation, first equation had x1 and x2 in it. The second equation had x1 and x2 in it. But through this change of variable, we have decoupled these equations so that first equation does not deal with Q2, and the second equation does not deal with Q1. There we are, decoupled. That's what makes this whole process tick. Now, if you write the first equation, this is what you've got. The first 10 weeks of the course, single degree of freedom system. There's only one unknown here, and that's Q1. Single degree of freedom system. There's only one unknown here, and that's Q2. And if I find Q1 and Q2, and I can do that, I mean, 10 weeks of the course, we have done things like this, okay? And then once I find Q1 and Q2, then obviously I go and find the X, okay? These are things that we have already indicated what they are. I'm just adding this thing for completeness. This is basically kind of a review type thing. This is modal mass matrix. This is modal stiffness matrix, and what they are is P transpose MP. This is what M tilde is, and this is K tilde is P transpose KP. So, in the problem that I did a few minutes for you, I want to find the decoupled equations, okay? So we already found the frequencies. There were 2 and root 2. We already found the mode shapes. This was associated with omega equal to 2. This was associated with omega equal to root 2, okay? And basically, I'm going to put that thing in your matrix P. This is modal. This is modal matrix. Okay. And if I do P transpose P and P, I better get a diagonal matrix, and I do. If I do P transpose KP, I better get a diagonal matrix, and I do. I've done use MathCAD here in order to work these out. If you want, just literally sit down and work it out. Okay. Now, remember, I arbitrarily chose the second component of both of these mode shapes to be +1. What if I use something else? What if, for example, I used for, let's hypothetically say for U2, I used 0.3, I get a U1 which is 0.1, etc. So what I'm saying is that I arbitrarily found this modal matrix because the choice of the mode shape was arbitrary, entirely arbitrary, like that, okay? Instead of 1 for this, I could have choose negative 0.3, and of course, if you do that, you're going to get 0.1 up here. The point is that, what if I use different modal matrix? Well, work it out. The numbers are going to be different. But one thing you realize is that 8 over 2 is 4. 0.72 over 0.18 is 4. 4 over 2 is the same as 1.44 over 0.72. The point is that the frequencies, the decoupled equations look like that for the top one. And if I had used this matrix P, the equations, number-wise, they look different. But look at the ratios. 0.72 over 0.18 is the same as 8 over 2. 1.44 over 0.72 is the same as 4 over 2. The point is that the decoupled equation, although the numbers may look different, but it'll give you, we have the same frequency here. You can see that. Okay. All right. Okay, so we want to continue with this particular problem and solve the equation of motion for the given initial condition. Now you might say, why am I doing this thing again? Because we have already found the natural frequencies of it and the mode shapes, and we have already decoupled them. Okay, it's just that we now have initial conditions that we want to solve the resulting equation of motion. Okay. Let me remind you that the modal matrix came out to be this 2 by 2 matrix. The first column was the mode shape associated with 2 rad per second, and the second column was the mode shape associated with the frequency of root 2 rad per second. We have already done this. And the change of variable in order to decouple these things is the good old modal matrix times the modal coordinates. So we're going to abandon x of t in favor of the modal coordinate. X of t are the physical coordinates, which means x1 and x2, and q of t are the modal coordinates. And look, there is no intuition or there is no physics which gives this is strictly mathematical operation, change of variable. Now, because we want to find the initial conditions in terms of q, I need to find q of t in terms of x of t, because initial conditions are actually given in terms of x. Therefore, I need to get it in terms of q, which means you just have to multiply this thing by the inverse of p, and this is what you're going to get. All right, so inverse of that matrix is right here. Now, when t is 0, we know x of 0. Okay, it's given here. And if you differentiate this thing, you can get when q dot of 0 in terms of x dot of 0. So let's go ahead and do that. First of all, we already did this thing in the previous example. We uncoupled the two equations, and they came out to be the first equation, which has nothing to do with Q2, and the second equation, which has nothing to do with Q1. I want to remind you that the frequency of the natural frequency of this single degree of freedom system, this is single degree of freedom system, is remember this 8 over 2 is going to give you square of the 2 rad per second, and this is 4 over 2, which is 2, the square of root 2 rad per second. So this ratio and that ratio are going to lead us to the natural frequencies that we got in the first place. Okay. Now, and this is exactly what I just said. If you go back to that uh, uh, PowerPoint that I created, it was called Mother of All uh, Equations in Vibrations. You see that the solution to this, and this goes back to week 3, week 4, and then we summarized them in that one PowerPoint, which was called the Mother of All Equations in Vibrations. It looks like this. Okay? The solution to the single degree of freedom system is right here. Of course, D1 and Phi1 depends on initial conditions, and D2 and Phi2 depends on the initial conditions. So, in order for me to find the solution to this, I need to find Q1 of 0 and Q2 of 0, which are the initial condition associated with this decoupled system. And how do you do that? You just go back here, say Q of t equal to P inverse of x, and Q dot of t equal to P inverse x dot of t. Now you plug in t equal to 0 and Q in both of these, and you're going to get the initial condition in terms of the modal coordinates, okay? So it's just a matter of literally putting the value of x of 0, which was 1 millimeter and 0, and literally putting the initial condition in terms of velocity, which was 0, 0, we get this. So now we have a single degree of freedom system. We have initial conditions. So Q of 0 is minus 1.5. Q dot of 0 is 0. Please go ahead, check your notes from 3 weeks ago and find a solution. There's no magic way of doing it. You just have to go to those solutions and plug them in. Okay, and if you do that, remember Q based on this, Q1 of 0 is just minus 1.5 from previous slides. You can see that right here, minus 1.5. And Q dot of 0, of course, is 0. And Q2 of 0 is 1.5. And I'm doing it by brute force. I'm not even using those formulas. If I don't have to, I can do it literally by brute force. Here is Q1. Q of 0 is this. Q1 of 0 is this. Q2 of 0 is right here. Q1 dot at 0 is 0. Q2 dot at 0 is 0. And just by brute force, find D1, D2, Phi1, and Phi2. Okay? Or use those formulas that we have from 4 or 5 weeks ago. Okay? So you solve it, and this is what you're going to get. And we have the solution for Q1 and Q2 because we found D1, V1, we found D2 and Phi2, and then just plug it in. And finally, you can get X by saying, remembering that X is related to Q by this expression. Okay? Just putting matrix P here, putting my solutions based on these things that I got here. You have Q1 of t and Q2 of t, and just work it out. And this is what you're going to get. Okay? Now, notice that because both of these phases are pi over 2, I can write these in terms of cosine. So it looks like that. And if you plot them, you won't be surprised. This is exactly what we got for the solution to the problem, the same problem we did in Tuesday, lecture 18, but not using the decoupled equations. Okay, uh, I just did it in a different way. Okay, now there was a mistake in one of the plots that I had uh, done there in lecture 18. One of the students pointed out to me, and I realized that there was a mistake in the X2 that I have in lecture 18. Okay, so there we are. Now, we see now. I also wanted to remind you that when we did this thing in lecture 18, I did not use the decoupled equations, okay? I just solved it by brute force. Brute force, and here we have decoupled it is more systematic, and either way. Now, okay, so this is a problem that I looked at in the previous lecture. So you're looking at the two degree of freedom model of a car, which involves a bounce and pitch motion. Now, in the lecture 18, I assumed that also there was dampers present at the two wheels, as you can see here. But in the present problem, we're going to assume that the damping is small, and therefore we're not going to take into consideration. The other thing is that if you look at the direction of x of t and theta of t are completely different from what was done in lecture 18. Therefore, we should not just go ahead and blindly take anything that we see there and bring it over and solve the problem. Okay? As a matter of fact, I'm getting this thing for you from the fundamentals. Actually, the fundamentals are fairly simple. It's just sum of all the forces in the vertical direction equal to mass times acceleration, and sum of all the moment about the mass center is equal to I about the mass center or J about the mass center uh, uh, times theta double dot. Okay. Now, so what I've done here, we are assuming x goes up, theta goes counterclockwise, as you can see here, and therefore the new configuration of this horizontal chassis is going to be like so. So the opposing forces are actually the spring force here and spring force there, and the moment arms are, well, the displacement actually, if you look at this problem, if assume that this thing goes up by some amount, the amount of stretching of this spring down here is x plus b times theta. B times theta will give you this much, but the whole thing goes up by x, so x plus b theta, and the other one is x minus a theta, because I'm assuming that this thing turns counterclockwise, therefore this end goes down, and therefore the amount of stretching is just x uh, minus a theta. Okay, and now uh, basically the free body diagram is shown here to you. So this is the spring force on the right, this is the spring force on the left, and uh, these lengths I assume that this piece is A, this piece is B. If you look at the one in lecture 18, I use different labels here. As I said, we should not be blindly going and copy this thing. I call this thing L2 and this one L1, but here it's going to be B and A. Okay. Now, drawn for you for simplicity, for uh, completeness. So sum of all the forces in the vertical direction is equal to mass times acceleration. Well, mass times acceleration is just mx double dot, and the forces are opposing, therefore they're drawn downward, and therefore negative here. And you take moment counterclockwise, look at this will give you a negative moment about the mass center. You can see that based on positive being counterclockwise. That's why this guy has a negative sign there, okay? Where this fellow gives you positive moment, okay? So that has a AK, uh, this is moment arm is, I'm assuming that you're talking about small deflections, okay, small deflections. So moment arm is A, here moment arm is B, and the force is drawn. You're assuming a small scale deflections, okay? So therefore, the moment arm is A and moment arm is B. Now, if you write this thing in the matrix form, it's going to be the mother of all equation, m vector x double dot plus k vector x. Now remember, vector x has two components in it. One of them is actually literally displacement vertically up, and the other one is rotation counterclockwise. So just be careful that vector x is not all translation. One component of its translation, the other one is rotation. And the mass matrix is obvious. You rearrange this thing, it's going to be the mass of the car, think about it like that. And this is J is the whatever the moment of inertia about mass moment of inertia about the mass center is. Now here's the data that's given to you. We just plug it in. And the matrix K, by the way, you just clean this up, it's going to look like that. And this is consistent with what we had in lecture 18, except that, you know, the direction of these displacement rotations are different, okay? But consistent with that. There's no damping here, so you don't have to worry about it. Just plug in these values, and this is what we're going to get. Now, the rest of it is just, you really need a calculator to do that because it's going to be ugly. These are ugly numbers. And here's your characteristic equation, determinant of this thing equal to 0. Okay. And just literally you have to work it out. You put it in MathCAD, put it in MATLAB, whatever you want. It's going to be very prone to error if you do it manually. Okay. So we have omega 1 and here's omega 2. For each one of them, you have to plug it in there, find the mode shapes. Okay, so let's say 10.7. You plug it in there. Omega 1 is 10.7. Patiently find U1. Remember, there is a degree of arbitrariness involved here because this is really not two equations, it's one. So this is the two equation, but they're not independent of each other. One of them is a multiple of the other one. And by arbitrarily, you're going to set U2 equal to 1, quite arbitrary, and you're going to find U1, and there is the first mode shape, okay? Or the mode shape associated with 10.7 rad per second. And again, now you take omega equal to 19.341, solve this equation, plug in your numbers, arbitrarily set U2 equal to 1, find U1, and there is the mode shape associated with the frequency 19.341 rate rad per second. Now, we have the modal matrix if you want. So you take the first mode shape, put it in the first column, second mode shape, put it in the second column, and you can check if you do the multiplication P transpose MP, you better get a diagonal matrix. And well, it's almost diagonal, but it is diagonal because these are powers of 10 to the minus 12. 0 for all practical purposes, and 10 to the minus 9 for all practical purposes. And therefore, if I take rounded off, your modal mass matrix is going to be right here, and your modal stiffness matrix is going to be there. Please realize that you cannot get these things by physical argument or intuition. You just have to work it out. There's no other way. Now, if you want to write the uncoupled equation, you have to make this change of variable, right? The usual change of variable. And if you do that, you have two independent decoupled equation, one involving vertical motion, the other one involving counterclockwise rotation. And these are the uncoupled equation. Now, if somebody gives you initial conditions, Then just like the previous example that I did, you have to find Q1 at 0, Q1 dot at 0, Q2 at 0, Q2 dot at 0, just like the previous example. Okay? And then how do you get those initial conditions? You just plug it in there. You need to invert the matrix P in order to get the initial conditions. And then, just like the previous example. And that's pretty much it. We're not going to do it. We're just going to leave it the way it is. All right, folks. So, yep. I cannot uh, claim that this, I will not claim that this is all based on intuition. Really, to do problems like this, you need a package. I mean, if the numbers are extremely nice and round, etc., like the previous case that we looked at, remember the two masses horizontally vibrating, etc., then numbers are round, still manageable. But once you go to real problem, these you have to use a utility package such as MathCAD or MATLAB, reluctantly Excel in order to get the stuff that you want to. Okay. Now, when we come back. Next week, I'm going to solve the problem. This was all free vibration. We're going to look at the case where there is a force acting, and I'll show you how to solve problems where there's a force vibration. Okay, that comes next week. Good luck. Just a reminder: the quiz, which is coming up next Tuesday, will not cover the stuff involving 2 degrees of freedom / multi degrees of freedom system. Okay, that is going to come on the final exam. Good luck.